we're looking at the different effects of scale and how it basically costs us money and damages metal and under deposit corrosion and overheating, and we introduced terms like top dryness and departure from nuclear boiling, and saw how it affects circulation and all this kind of neat stuff. And we also talked about how it got into the boiler. So maybe it was through a leaky heat exchanger in a domestic hot water heating vessel. Maybe it was condenser water entering into a turbine, a condensing turbine condenser. So there are lots of different ways that we can get scale. Even if we are very vigilant, we can still get scale appearing, scale forming compounds appearing in the boiler. So we got to deal with it inside the boiler. So our boiler is going to be a little chemical factory. So there are really two ways that we deal with scale that gets into the boiler. And number one is precipitation softening, and number two is solubilization. Now, you know what precipitation softening is, right? We talked about lime, and we talked about soda ash, and you think, okay, we did that in a lime soda softener, and that seemed to be pretty good. So why don't we add lime and why don't we add soda to a boiler? Because we don't. So what is lime? Calcium hydroxide. Oh, that'll work. This will take care of any temporary hardness that leaks in, but we are adding hydroxide, and too much hydroxide is a bad thing. Too much is bad. So we don't want to add all this extra hydroxide into the boiler. We're going to get caustic embrittlement, we're going to get under deposit corrosion, caustic gouging, blah, blah, blah. So we don't want to add calcium hydroxide. Well, what about the soda ash? And there was a time, a long time ago, maybe say 100 years ago, soda ash, the so-called soda, is Na2CO3. And yeah, we can use this to deal with some hardness that enters the boiler. But the big problem here is what this does to alkalinity, because CO3 is alkalinity. And we don't want too much alkalinity, because too much alkalinity, number one, will cause foaming of the boiler water and priming, that sort of thing, where we start to get water into the steam. But also, very importantly, alkalinity will decompose in the boiler. It'll produce carbon dioxide gas, and the CO2 travels with the steam, and then in the condensate system turns into H2CO3, which is carbonic acid. So alkalinity is going to cause us return line corrosion. So we like to limit the amount of CO2 potential, and we like to limit the amount of hydroxyl that we add to the boiler. In other words, we're not going to use lime, we're not going to use soda, but what we are going to use is a phosphate. And phosphate ion is PO4 3 negative. So we can have a few different types of phosphates that we add. We can have sodium monosodium phosphate. We can have disodium phosphate. And we can have trisodium phosphate. So what do these have in common? Sodium, 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 which means that they are very soluble. And they don't precipitate, they don't form scale. The other thing they have in common is phosphate, phosphate, phosphate. And so the PO4 is going to combine with the magnesium, and it's going to combine with the calcium to form insoluble precipitates. like seriously insoluble precipitates. So it's like we did before um, in the lime soda reactor, but instead of using lime or soda, we're going to add phosphate. What we end up with is calcium and magnesium phosphate compounds, and they're going to precipitate as these tiny little particles. And so then what we have to do is prevent these particles from baking on. So there are two kinds of scale uh, things that go on. And the first one would be precipitation. And precipitation is when the scale forms directly onto the heated surface. And then the other thing that we can do is deposition. And deposition is after the scale precipitates have formed. Uh, the, uh, the precipitates can form a sludge, and it gets baked on to the heating surfaces. Baked, I'll put that in quotations. Baked on. So two sort of scale processes. One is precipitation, the other one is deposition. So here, this is a softening mechanism where we precipitate insoluble compounds. But if these precipitates aren't dealt with, then they will deposit. So we don't want the precipitates to deposit. So we're going to add some other chemicals to our boiler as well. We're going to add a sludge conditioner. And the sludge conditioner will make sure that any precipitates that form aren't sticky. And then what we want to do is keep everything well dispersed in the boiler water so that we can blow it off. So these two things together, the sludge conditioner and the dispersant, they permit us to blow off the sludge. And what's the sludge made of? Calcium and magnesium phosphate. Then the next method is to use something called a chelant. Now, this solubilization then is the exact opposite of precipitation softening. They're like opposites. You see, because precipitation, we make the stuff come out of solution. Solubilization, we keep the stuff in solution. We turn the calcium and magnesium into highly soluble compounds by adding EDTA, which is one form of chelant, and NTA, which is another form of chelant. And so what these things will do is combine with calcium and magnesium and iron and copper and other things too. But the main purpose is that we want it to combine with our calcium and magnesium compounds and form a highly soluble compound that will not precipitate. Ain't that neat? So they're really kind of like opposite processes. So as for the precipitation softening, we're going to add a couple of different types of phosphates, and each phosphate is going to do something that's a little bit different. So let's first of all look at the monosodium. It's only got one. The monosodium phosphate, when I add it to the boiler water, it will actually combine with sodium hydroxide and give you disodium phosphate and water. Okay, big deal. If we add disodium phosphate to sodium phosphate, again, it will find hydroxide and it will consume with the sodium hydroxide. It will consume to form trisodium phosphate and water. So these are not precipitation reactions. Okay, these are not precipitation reactions. We're going to get to that next. And if we add trisodium phosphate to the water, it'll react with the water itself and it'll form disodium phosphate and sodium hydroxide. So let's take a look at what's going on here. We want to make sure there is phosphate available. So let's just take a look at the products. The products are all on that side. And so here we've got a disodium phosphate. We've added monosodium phosphate. And we get disodium phosphate. Yippee skippy. The main thing is we've got the PO4. That's what's going to do our reacting. If I had disodium phosphate reaction and then on the product side, I still get a phosphate. Yippee. I add trisodium phosphate. What do I get? I get a phosphate. So, moral of this story is adding any of these adds phosphate to the water. It says Amy. Adding Amy or any of them to the water increases phosphate. And we're going to want to have a certain amount of phosphate in the water because that's getting rid of the magnesium and the calcium. So this is a good thing. Now, what else do we got in the product side? We've got sodium, we've got sodium, we've got sodium. And what we know about the sodium is sodium compounds are highly soluble and do not form scale. So we're adding in sodium compounds, and we've got sodium compounds coming out, and so we're not adding any kind of scale-forming compound. Okay, this stuff is highly soluble. Now let's take a look at some of these other products that we got going on here. We got water. Okay, that's good stuff. More water, more good stuff. Oh, we've got sodium hydroxide. Very interesting. So let's now take a look at this chart to the right. And this little chart is from the Suez handbook that you can find online of industrial water treatment. Very, very important book. And so let's see what they say about these three phosphate species. First, let's take a look at what we see on the y-axis. On the y-axis, we've got pH. And as for the x-axis, we've got parts per million of PO4. Okay, so increasing phosphate concentration and increasing pH. So let's first of all say I've got a boiler and I'm operating at less than 900 psi, and that would be about 6.2 megapascals. Somewhere around there. So, oh, look at this one here. This one here is 6.2 megapascals to lots of megapascals, and higher pressure and higher pressure and higher pressure, right? So what we have here is a series of I don't know, what do you call that geometric shape? Rhombuses, rhombi, and these rhombi show a control area for pH and for phosphate given a boiler operating pressure, okay? So what this box, so let's say that I'm operating at less than 6.2 megapascals, sort of like our lab boilers are all operating at less than 6.2. So I have a control range, and that control range says, well, let's go right up here first of all. On the pH scale, we'll say that's about 10.7 is the pH of the water. And as for the phosphate, we got about 60 parts per million there. At this point here, we've got, let's say, 10.1, and again, 60 parts per million of phosphate. You get the idea, right? We got about 9.8 over here, and 30 parts per million. And here we've got about 10.4 and 30. And so what we have then is a control range. What we would like is to keep our pH and our phosphate residual somewhere in that range. So, and then of course there's other boxes, other ranges for boilers operating at different pressures. So let's say, for example, our boiler is between 1500 and 2000 psi. Right there, that's the sweet spot. We would like to have a pH somewhere around, close to 9.4, and a phosphate residual somewhere around 6. That's where we want to be. Now I'm going to do water tests. I'm going to find that my pH is about there, and my residual is about there. Well, I want to get into the sweet spot, so I want to sort of shift. I want to kind of like decrease my pH a little bit and increase my phosphate a little bit. Well, according to this chart here, if I want to increase the phosphate and decrease the pH, I can add monosodium phosphate. Monosodium phosphate has the effect of, and I'm going to resolve this into vectors now, of increasing the phosphate, because like I said, every single one of these affects phosphate. Every single one will increase the phosphate. And I also want to reduce the pH. Well, how the heck is this stuff going to reduce the pH? It reduces the pH by consuming sodium hydroxide. As you can see, that's what monosodium phosphate does. Ain't that neat? So using that same logic, let's take a look. Let's say I'm sitting over here somewhere. My boiler is at 1700 psi, and my pH looks like it's about 8.9, something like that, and my phosphate is around 4. And again, I want to get into the sweet spot somewhere right in the middle. So using that same logic, you tell me which of the 3 phosphates would I use to both boost the phosphate and boost the alkalinity. Anybody? Can you all hear me?
We can all hear you. I just don't know the answer.
Okay, so what we're going to do is we're just going to look at this chart here, and if I want to increase the pH and I want to increase the phosphate, here's another arrow. It's in the same direction, right? Trisodium phosphate will increase the amount of phosphate, and it also increases the pH. So let's go over here. Trisodium phosphate, Na3PO4. What does it do? It combines with water. It increases the phosphate, and it releases sodium hydroxide. It produces sodium hydroxide. Sodium hydroxide has a high pH. So in other words, by producing hydroxide, you increase the pH, and you increase the phosphate. Okay, so we've got two examples now. This one here you should get. Okay, this one here you should get. I'm not going to help you out much. Same boiler, but you know, my pH is pretty good. My pH is right here at the sweet spot, but my phosphate's too low. I want my phosphate to be somewhere in the middle of this control range. So I want to increase the phosphate, but I don't want to affect the pH at all. Which one would I use to increase the phosphate without increasing or decreasing the pH?
Disodium phosphate.
Bingo, disodium phosphate. Okay, so if I had disodium phosphate, let's take a look at this one here. It consumes hydroxide. It produces trisodium phosphate, and the phosphate is good. We want the phosphate. But you're going to say, oh, it consumes hydroxide, so it should actually lower the pH. But this is the tricky part. This is an equilibrium reaction. So it reaches a point of equilibrium. So though we are producing trisodium phosphate, that trisodium phosphate, as it's produced, combines with water and gives you disodium phosphate and sodium hydroxide. So the disodium phosphate consumes sodium hydroxide, but once it becomes trisodium phosphate, it releases sodium hydroxide. It's like it breathes in, it breathes out, it breathes in. And so even though it consumes sodium hydroxide, once it converts to trisodium phosphate, it releases sodium hydroxide, so it has a net zero effect on the pH. Okay, so those are the three phosphates, and that's the type of effect that they're going to have. Ultimately, what you're going to be adding to your boiler will be a blend of 2 or 3 different phosphates in different combinations, depends upon your plant. Basically, how much makeup water do you have? How much condensate returns do you have? What's in your condensate returns? What's in your makeup water? And all this kind of stuff. And then what is going to happen is a water treatment rep is going to say, how do we keep you in the sweet spot? Okay, we're going to keep you in the sweet spot by adding, you know, a blend, and each one of those phosphates is going to have a slightly different effect. What you got to get out of this is that monosodium decreases pH. Disodium has a neutral effect on pH. And sodium hydroxide, or pardon me, trisodium increases pH. And so, you know, we think about pH in a boiler and go, oh, I do a pH test and go, oh, my pH is low. What am I going to do to raise the pH of my boiler? And a lot of people say, oh, I'm going to add sodium hydroxide. But it might not be necessary. If you want to increase the pH of your boiler water, do a phosphate test first. You do your phosphate testing. Oh, my phosphate's low. Oh, I know what I got to boost my phosphate. Yes. And I want to increase my pH. Okay. So which of the 3 species is going to increase my pH and my phosphate at the same time? Well, that would be the trisodium. Increases pH and increases phosphate. So But like I said, your water treatment rep is going to have a handle on this. They're going to know what's coming in and all this kind of stuff, and what you're going to want in your particular blend to keep you somewhere right in the middle of the control area for your particular boiler. Then, we may want to increase pH only, and for that we would add caustic soda. Okay. And blowdown is also shown on this vector diagram. Blowdown has the effect because it dumps water from the boiler, right? So if it's going to dump water from the boiler, the blowdown, and again resolving this into vectors, is going to lower the phosphate, and it's also going to lower the pH. Just because we're getting rid of this stuff that's in the boiler and replacing it with fairly pure water in our makeup. So that then is this chart here, and you can go to that website. I highly encourage you to go to the Suez Handbook of Industrial Water Treatment. Has anybody gone there yet? Well, when you're studying your second, that's where you want to go. Anyway, so because we're coordinating things, right? We coordinate the blend. How much of this is in the blend? How much is that? How much of that? And then also alkalinity. How much caustic do we have to add, if any? What we call this then is a coordinated phosphate treatment. And it's discussed in your textbook, but they kind of allude to it. And they sort of allude to this diagram. They talk about a molar ratio of 3:1 sodium over phosphate. And you'll see that that's not actually really what we want to do. But that's as far as I'm going. Now this is the good stuff. This is the reaction. So trisodium phosphate is the only one that I'm showing here. Yeah, so trisodium phosphate. Here are some 3 representative hardnesses. Notice you got magnesium and calciums. Anything with magnesium, anything with calcium is hard. Then we've got species here that are permanent hardness, sulfate. We've got a chloride that's a permanent hardness, and we've got bicarbonate, which is a temporary hardness. So what do we got going on here? These are basically double replacement reactions. We're going to take the sodium and swap it for the magnesium, or we're going to take the sodium and we're going to swap it for the calcium. Okay, just a double replacement reaction. So what we end up on the product side is sodium phosphate plus magnesium sulfate gives you magnesium phosphate, which is a precipitate. It is insoluble. And sodium sulfate, which is highly soluble. This stuff remains in solution. Maybe I should put like an AQ there, hey? Remains in solution, in an aqueous solution. Being a sodium compound, it's highly soluble. It doesn't precipitate, it doesn't make scale. But it is a dissolved solid. So, whatever. We know how to deal with dissolved solids. So we got calcium chloride here and trisodium phosphate. We end up with calcium phosphate. Again, it's a precipitate. And we get sodium chloride, which we know we sprinkle on our French fries. Again, remains in solution, non-scale forming compound. And the next one we have sodium phosphate plus magnesium bicarbonate. Being temporary hardness, we get, again, magnesium phosphate, precipitate, and sodium bicarbonate, or baking soda, as an aqueous in solution. Again, all sodiums, highly soluble, do not precipitate, do not form scale. This one here is a bit of a problem, because not only is that a dissolved solid, but that is bicarbonate alkalinity. And bicarbonate alkalinity yields CO2 potential, which gets into our condensate return and forms carbonic acid, which eats our condensate return lines. So it's there, but we're going to deal with that. We're going to, when we get into corrosion, we'll see that we have amines that we add to the boiler water, and they can take care of that carbonic acid that may form. So those are the precipitation softening reactions. Now we're going to make this stuff, and we don't want it to be adherent. So again, we're going to we're going to have to add some sort of a polymer, and the polymers can be dispersants, and they can also be sludge conditioners. And the whole idea is that we make sure that we are making a product that isn't sticky. So take a look at this crystal here. This is a calcium phosphate, I think. It says calcium phosphate magnesium silicate, so I guess both of those crystals are present. But if you take a look, this is one of these phosphate precipitates, and it's like Velcro. And we know what Velcro is. And so this stuff is going to adhere to the boiler heat transfer surfaces. And we said that, scale can directly precipitate, yes, or we can get deposition. Well, this stuff here, if it sticks to the boiler metal, we're going to get deposition, a deposit. It's going to have a similar effect like scale. So what can we do about that? Well, we can add a sludge conditioner, and these polymers have the effect of, and so now instead of it looking like Velcro, this is the same crystal, but this crystal is different shape. It's no longer Velcro, it's more like Tic Tac. You know what Tic Tacs are? Breath mints. Okay, so they're and so you can see they don't have the Velcro on them anymore. So basically, what we add is a compound that changes the way the crystals grow. The crystals still form, they still precipitate, but they take on a different shape that is non-adherent. So that's basically what sludge conditioners do. And the dispersants basically keep things well dispersed in the water so that continuous blow down and bottom blow off can actually discharge it from the boiler. Now, yeah, I went over that one. Just want to go back and make sure. Now, there's one other thing that, this is a term, this is mentioned in your textbook, okay? And that's why I'm going over it. But you're going to read other books, and they're going to have a name for this stuff. This is calcium hydroxide and phosphate as a single precipitate. So we like to think, oh, we're going to get a Ca3PO4 twice. That's what we think we're going to get. And this ain't the greatest kind of stuff because it is kind of sticky. Sticky-ish. There's one that's even more sticky than that. This one here, Mg3PO4. This one here is quite adherent. Okay, so we actually don't like this one to form. But this one here is kind of sticky as well, and we don't want deposition. So if we've got free available hydroxide, we've got adequate hydroxide in the boiler. We know we usually do, right? We do 2P minus M is equal to our OH alkalinity. You know, we do take a boiler water sample, we do the P alkalinity, and then we do the M alkalinity, and we do a little bit of math, and it tells us how much hydroxyl ion is in the boiler water, and maybe have, say, 150 to 300 parts per million of hydroxyl alkalinity. Okay, maybe that's our control range. And why do we do that? To control pH, so we don't want any acid attack in the boiler. But here's another really important reason to have OH alkalinity, because it will make a hydroxyapatite. So hydroxyapatite is the name for that stuff there. That's its name. Now, your textbook doesn't use the name, but I'm using the name. I'm giving you the name. So when you're reading a technical bulletin and they talk about hydroxyapatite, now you know what it is. So it's a calcium phosphate precipitate, but it's a calcium hydroxide phosphate precipitate. Why do we like it? Because it's not like Velcro. It's more like this. So if we're forming hydroxyapatites, that's the better form of precipitate because we will use less sludge conditioner. Now, then there was another kind of yucky scale that we didn't like too much. Actually, this again is a precipitate, Mg3PO4 twice. And this one here is kind of sticky. Again, if we have got hydroxyl available, we can precipitate magnesium hydroxide, which is preferred. And you've seen magnesium hydroxide with the lime soda softener, because magnesium hydroxide is a floc, right? Flocculating agent. So it actually helps in terms of what's going on with the formation of particles. It's not sticky. It helps get the particles to kind of come together in terms of like making a sludge. And then that sludge is going to go to the mud drum. It's easy to blow off. Okay, so what we have now here is 3 good reasons to have just the right amount of hydroxide. First of all, for pH control. Secondly, to form a hydroxyapatite. And thirdly, so that magnesium precipitates into a less sticky form. Whew! Boy, oh boy. That was a lot. So, what do you got to get out of this? You should know what the reactions are between trisodium phosphate and various, hardness magnesiums and calciums. You should know that OH helps out with pH control and also helps form the hydroxyapatite, and also helps form the non-adherent magnesium precipitate. You should know that a coordinated phosphate treatment is going to coordinate different blends of phosphate that'll be added to your boiler, and coordinates that along with pH and blowdown, because all of these things here are working together to keep you in a sweet spot in terms of your phosphate residual and your boiler pH. You should know that some phosphates will increase your pH by increasing OH concentration in the water. You should know that certain phosphates consume OH in the water, and you should know that certain phosphates have a neutral effect on the OH in the water. So, next thing is phosphate hideout. So let's say that I have got a boiler and I get a call from system control and says, I need more megawatts. So what I do is I start firing the boiler harder. I bring on, another pulverizer, bring on another row of burners. And what I do is I increase the firing rate. So maybe I'm, first of all, operating at 50,000 kilograms per hour. And then they want me to increase the firing rate to 100,000 kilograms per hour. I'm making more electricity now, okay? In doing so, I've increased the heat flux through the boiler tubes, and right at the very surface of the tube, I have caused a certain amount of dryness, if you will, for lack of a better term. So we're going to get some sodium phosphate that's going to come out of solution and kind of get stuck to the boiler walls. It's not scale. It's very soluble sodium phosphate, but it's stuck on the tubes and it's not involved in the water. So by increasing the firing rate, I've taken sodium phosphate out of solution. And so then I do a water test. I'm at 100,000 kilograms per hour. I do a water test and go, oh, what happened to my phosphate? My phosphate is gone. So then I add more phosphate and I get back into the sweet spot area. Well, a couple days later, they say, oh, we don't need all that electrical generation, and so we need you to back off. So we take our firing rate from 100,000 kilograms per hour, and now we're down to 50,000 kilograms per hour. And we find that all that phosphate that sort of kind of disappeared on us returns. And so this is a phenomenon called phosphate hideout. Because always keep in mind that the sodium is highly soluble. So even though it kind of hides on the tubes during a high firing rate, it will resolubilize at a lower firing rate. So the point of this is phosphate hideout makes phosphate residual difficult to control when you are not at steady state operation. Okay? So this may make chemical control difficult when not operating at a steady state. Now this is mentioned in your textbook, so phosphate hideout must be one of those terms that you kind of need to know. Okay, you need to know the term, you need to know what causes it. So before I go on a break, this one's pretty easy. This is solubilization. Chelants like EDTA and NTA. And basically what we have is, here's a metal. This metal is face-centered cubic calcium. And, we've got these atoms on that face-centered cubic unit cell structure. And then here is our EDTA. And notice that it has these tentacles. I'll call them tentacles. So, and the tentacles end up with COO and a little charge there. COO and a little charge. Even though that says OOC, that's just like a mirror image, right? And so what's going on? Well, these tentacles here are going to, there's our metal. And so let's take a look this way. There's our O. There's our O. The O bone's connected to the CO. There's our CO, which is connected to the CH2, which is connected to the CH2, and then to the amine. So then we've got another one here. Goes to the O, goes to the CO, goes to CH2, goes to the amine. And so this is just really to demonstrate to you that these tentacles here are going to connect with the various points and basically knock the calcium or the magnesium kind of out of action. Basically makes them non-reactive. The reaction has taken place and what you formed is something that's super soluble. So this is the alternative to precipitating. We solubilize. Now the nice thing about it is it's indiscriminate. So if I've got a boiler, here's the inside of the boiler, and it's got a whole bunch of pre-existing calcium and magnesium scale. And I got feed water coming in. Okay, if I do feed water analysis, I know that I got so much magnesium going in there, and I got so much calcium going in there. And so I'm going to very, very carefully control how much, oh, beautiful, now I lost my, there we go. Okay, I'm going to very, very carefully control how much amine I put in. And the quantity of amine, and this is ethylene diamine tetraacetic acid, so I should really be calling it chelant. The amount of chelant that I'm adding is going to be just enough to knock out that stuff. No more, no less. We want the exact amount. But if I overfeed chelant, then it's going to go into my boiler and it's going to look for other metal ions. Oh, it found some calcium and magnesium on the scale. So it's going to suck the calcium and magnesium from the scale, which is going to cause the scale to loosen up and to soften and to fall off. So the neat thing about adding chelant, it can remove existing scale, but only if we overfeed it. So that's fine if you got existing scale, but we don't want this to go too fast, because then we're going to get large chunks of scale going into the downcomer, bottom header. It's going to block off flow. It's going to cause flow restrictions and things like that. And then the other thing is, what if it doesn't find any calcium magnesium? What if the calcium magnesium is removed within the first month or so of overfeeding, but you keep overfeeding EDTA? Then the chelant is going to find other metals to combine with. So it's going to find, let's say, some magnetite. And magnetite is Fe3O4, which is a protective layer of iron oxide. Well, then it's going to start combining with the iron, and it's going to eat away at the magnetite layer, which is then going to expose bare metal, which is going to corrode. So chelants are non-discriminatory. They will attack iron, they will attack calcium, magnesium, whatever metal is around. So we have to be very, very careful if we are overfeeding chelant in order to remove scale. Okay, very, very careful, because we don't want magnetite attack. So the other thing is, if I am exposing bare metal and maybe I'm eating away at magnetite, if there's any dissolved oxygen in the boiler, any of it, it will kill my boiler in a short period of time. O2 becomes extremely aggressive to boiler metal at the high temperature that exists, and if there is no protective magnetite. So, whether we are in a solubilization routine or a precipitation routine, or maybe both, we can use solubilization plus precipitation at the same time. Okay, it really depends what your water treatment rep does. That's why we have these smart chemical reps who do this kind of analysis for us. But okay, so the next thing is these polymers, these sludge conditioners and dispersants. Now, back in the olden days, we had these things called tannins and lignins, and you might recognize the word lignin, like lignite coal, or then you might know tannins if you know something about wine drinking or tea drinking. So tannins and lignins were added 120 years ago to boilers because they figured out, hey, we actually get less scale deposition. So let's take a look at these 6 slides here. So this first one here is the phosphate cycle, okay, coordinated phosphate with no, and I should say, conditioner or dispersant. No sludge conditioner, no dispersant. And so what do you get after a period of time? You get deposition. So yeah, you took care of the scale, but you didn't prevent it from depositing. And then say, oh, if we use a natural conditioner, like a tannin and a lignin, we actually got less scale deposition, a little bit cleaner. And then this one here is phosphate cycle with a lignin, a little bit cleaner yet. This one here is a phosphate with polymer. So now we have these new fancy, we don't use tannins and lignins anymore. We use sulfonated and carboxylated polymers, whatever the heck that happens to be, right? So, but the whole point is that we can prevent that deposition. So that's like a pretty clean tube. These are water tubes, by the way. No, pardon me, fire tubes. I'm sorry. But obviously that's the external circuit. You're looking at the water side of the tube. And so then here is one that has both phosphate and chelant together with a polymer dispersant. This one here is only a chelant plus a dispersant. So point of the matter is how we combine polymers, chelants, dispersants, phosphates, all that kind of stuff really depends upon your water treatment rep, and they will assign the best treatment program for your particular boiler. And usually something that has to be cost effective too. So that's it for scale control. So now we're on to corrosion. And just to remind you that a lot of the stuff is in the corrosion chapter that we already looked at. So I'm not going to spend a lot of time on corrosion, but I do want to look at magnetite. And this is stuff that should come back to mind. We said that certain materials, so for example, chromium develops a passivating oxide layer that prevents further corrosion. So what we call a pacifying oxide. Pacifying oxide or passivating oxide is something that makes a non-porous oxide. So in other words, nothing can get through it. It's like a barrier. So though magnetite is in fact an oxide, it's a product of corrosion. Because we had to take some iron and we had to oxidize it. Though it is a corrosion product, it is non-porous and it acts as a barrier and it prevents further corrosion. So, what makes it come about? Well, we'll take a look at a couple of reactions for the formation magnetite. We want magnetite, right? This is good stuff. We want it to be there. How does it form? We'll take a look in the next slide, I think. But just be aware that it is fragile in that caustic, excessive caustic or chelants can actually consume a magnetite layer. And if magnetite layer is consumed, well, it always rebuilds itself, right? But it rebuilds itself using what? The iron of the boiler shell. So we can say, it keeps rebuilding. Yeah, but it needs to find some iron to rebuild. And where does it get the iron from? The boiler shell. So if we remove the magnetite layer, corrosion continues and continues and continues. So we don't want excess caustic, and we don't want, if we're overfeeding chelate, we have to be really, really careful. So how do we form it? The two basic reactions are this one here, where we've got iron, which of course is in the steel, because you know the steel is primarily iron, and water forms magnetite and hydrogen. This occurs in the absence of dissolved oxygen. Another good reason for having your deaerator working properly, and also for chemical deaeration. Now we look at number 2 here, and hydrazine is just really an example. Hydrazine is an oxygen scavenger. And it works like this. I take hydrazine, and I've got some dissolved oxygen, and it gives me 2H2O plus nitrogen gas. Beautiful. It's a wonderful oxygen scavenger. So while it's busy scavenging oxygen, any excess hydrazine, any residual hydrazine, is going to combine with hematite. Now, hematite is what you have on your car. It's rust. And so it's already a corrosion product. It's an undesirable corrosion product. We don't want it. Well, hydrazine will actually convert it into magnetite and nitrogen and water. So there are certain oxygen scavengers. Hydrazine is one of them, and there are other ones called like hydroquinone is another oxygen scavenger that has a similar effect on the formation of magnetite. And carboxy I think it's called carboxyhydrazine. Just a few different O2 scavengers that not only get rid of the dissolved O2, because we don't want that present, but also help form magnetite. So then the next thing is what causes steam system corrosion. And I think in your textbook they call it boiler corrosion. But I think we've got to be careful. We call it steam system corrosion because dissolved carbon dioxide number 4 is not actually going to corrode our boiler. But this stuff here is going to corrode our condensate system. Whereas, of course, we know what dissolved oxygen is going to do. We know what high pH is going to do. We know what low pH is going to do because we've already studied this in the corrosion chapter. And so if you go back to the corrosion chapter, there's a section specifically on boiler corrosion, so that's a good thing to review. So this is a nice little chart. Again, it's from Suez. And it shows you the safe range for pH. So anywhere from about 9, that says 8.5, and that looks like it's about 9.5. I just noticed that for the first time. And this is 12.7. Let's call that 9.3. Okay, and so anytime our boiler water is somewhere in that range, corrosion rates are pretty low. So here we've got relative corrosive attack. I have no idea what kind of units that they're using, but let's say relative corrosive attack. You know, really what we're going to look at here is the slope of the line. Okay, a very steep slope indicates a high rate of corrosion. And you can see once you get down to around a pH of 3, you know, due to the low pH, a corrosion rate really picks up. And over, say, about 13 or so, or 12.7, again, the water becomes very aggressive. So what we're going to try and keep it between, say, 9.2 to 9.6. That seems like a pretty good number. Now, a common misconception people have is, if my pH is too high, or if my OH alkalinity is too high, what do I do? And some people say, add acid to the boiler. So you got a little acid feed pump, adds a little bit of acid. Never, 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 never add acid. If our pH is too high or our alkalinity is too high, there's a couple things we can do. Increase our CBD. And you know, that's continuous blow down. We can increase our bottom blow off. We can do both of those. Or we can add monosodium phosphate, because we remember that monosodium phosphate actually consumes hydroxide. Or what we can do is we can wait. That's the third thing we can do. I'm just going to add here, wait. So here's what waiting is going to do. Any excess hydroxide that we have in the boiler is going to combine with hardness leakage, and it's going to form magnesium hydroxide. I'm too close to the top of the screen here, so it's switching pages on me. So OH is going to, it'll be consumed. It's going to form magnesium hydroxide, or it's going to form hydroxyapatite. Or if we do get any low pH, acidic water coming in, let's put it this way, the low pH water will cause our hydroxide to fall. So if we wait long enough, the hydroxide, if it's not too far out of whack, will probably take care of itself. Now, where does the acid come in? Well, maybe we got a demineralizer, or maybe we got a dealkalizer, or maybe we got a SAC, or maybe we got a WAC, and each one of those is going to have some sort of hydrogen zeolite softening, which we regenerate it with H2SO4, and we got to make sure that we rinse it down after a regen. And if we don't rinse it down well enough, we will regeneration, sorry for the mess. We got to make sure it's rinsed down properly after the regen so no acid leaks through. Or maybe we got a dealkalizer, and the dealkalizer has got a hydrogen zeolite softener followed by a decarbonator, or degasifier if you want to call it that, or aerator. But to take care of the free mineral acidity, we are going to have a sodium hydroxide drip, just to get rid of the free mineral acidity. Well, what happens if our sodium oxide drip fails on us? In the plant where I used to work, we just had this crappy little valve, and we basically set this valve handle so that it would drip, say, like 1 drip every second. But what happens if that valve gets a little bit plugged up and it's now 1 drip every 10 seconds? Well, in such a crude situation, you might get free mineral acidity entering into the boiler. So this is one of the reasons why we like to have free hydroxyl ion available, because when the protons show up from the acid and they combine with the hydroxyl, we get H2O, right? They neutralize. So this is another one of these relative corrosion rates, but this time they're actually talking about parts per billion iron. And see, once your pH drops below 9.7, the rate, okay, so the rate would be identified by the slope of the line, and the rate of corrosion increases greatly. Wait a minute, I'm only at 9 here, okay? So, the pH doesn't have to change very much for the rate of corrosion to increase logarithmically, which only makes sense because the pH scale is a logarithmic scale, and we always have to keep that in mind. So if I went from, say, a pH of 9 to a pH of 8, you go, that's only a pH decrease of 1. But it's actually a 10 times increase in the concentration of hydrogen ions in the water, going from 9 to 8. So logarithmic scale, keep that in mind. Now, what else we got here in corrosion land? We've got, so this is the high pH business. This is the caustic corrosion. And here is an under deposit. The deposit's been removed so you can see the corrosion, right? So that's caustic gouging is one of the things, and that can happen under deposit due to wick boiling or steam blanketing. And again, if we got magnetite, then caustic will remove magnetite. And so then, though it's constantly repairing itself, the caustic could be continually removing the magnetite. So it's a problem. So how do we control pH? Well, coordinated phosphate program is very good at helping to control pH, simply because some phosphates combine with sodium hydroxide. There are equilibrium reactions that go on that tend to stabilize the pH of the boiler. And also with the coordinated phosphate program, not only does that stabilize the sodium hydroxide, it also prevents the formation of scale. And if I don't have scale, then I can't get under deposit corrosion and caustic gouging. Now the next one here is a form of stress corrosion cracking that you probably learned about last year a little bit, but now we know a little bit more about the crystalline structure of steel. And so here I'm highlighting the crystals, and they've got grain boundaries, and you can see how this grain boundary here, these grain boundaries have packed by hydroxide, by OH concentration. So how do we get this? Well, it's a form of stress corrosion cracking, so there must be stress, applied or residual stress. So take a look over here. I got a water tube. I know it's a water tube because it's got a flared end, and it's been expanded into a tube sheet, okay, using a 3-roll expander. And in expanding it, what I did was I exceeded the elastic limit of the material, brought about permanent set. It held tightly into its tube sheet, and so what we have is stress. Good place for corrosion cracking to occur. Now inside the boiler, I got some water that's got just the right amount of hydroxyl ion floating around in there. Just the right amount, 150 to 300 parts per million. I'm happy with that. But let's say I've got a tiny little leak, and the leak is so tiny I will not even notice it. I won't even see chemical staining. All I need is to have is enough of that normal concentrated water to go along that tube seat, and basically having all of the water evaporated, leaving a very high concentration of hydroxide all the way along that tube seat. Very high concentration. And so that gives us this one here, boiler water with a high concentration of sodium hydroxide. Well, how did that occur? Because we had a leak. So the leak concentrated the boiler water, concentrated the hydroxyl ion, and the applied or residual stress from the forming gave us caustic embrittlement. And of course, we know the brittle failure is sudden with no prior deformation. And we don't want that. Deformation. Okay, we don't want our boilers failing. And if it's going to fail, I want to see prior deformation, damn it. I want to see the tubes bulging. I want to see my steam drum bulging. I want to see my pressure gauge pinned to the max. And I want to be able to look at that expanding boiler and go, my God, I'm hightailing it. And I want to bolt from that boiler room as fast as possible, right? It's what does George Carlin say about in the bar? You know, it's the quiet ones you got to watch out for. You know, this one's not going to give you any warning. It's just going to snap and it's going to kill you. So we don't want that. Now, as for the oxygen, well, we know about this. Really, all this stuff ultimately is galvanic in nature. Even the stress corrosion cracking, it's all galvanic in nature. And all we have is a whole bunch of things that, you know, exacerbate or promote corrosion, whether it's dissolved oxygen or whether it's, you know, hydroxide or whatever the situation is. We just got something going on that is accelerating the galvanic corrosion. And that's what we see with an oxygen pitting, oxygen corrosion cell. So what do? We try and keep the concentration of dissolved oxygen really low, 5 to 7 parts per billion. How's it getting in? Maybe our deaerator is not working properly. Maybe you're not maintaining an adequate oxygen scavenger residual in the boiler water, and you're not maintaining an adequate residual in the deaerator, because we're going to add chemicals to the deaerator as well to keep that working well. But, you know, we've got makeup water, leaky heat exchangers, condensate return systems, lots of ways where we can introduce oxygen into the system. Now, you can see here the inside of a pipe that has got extensive oxygen pitting. And this surface has been cleaned again so you can see it, but I just want you to take a look. This is the cross section here. And so all of those little black blotches there, it's actually a pit. And one of the characteristics of oxygen pitting is it removes a very small amount of metal, but it removes it from a tiny location. And then basically it turns our boiler into Swiss cheese. Okay? And I don't know about you, but I don't like Swiss cheese. So I would say this stuff here is the #1 killer. And in case you didn't know, I was a boiler inspector for 7 years. And I would call this #1 killer of boilers is oxygen corrosion. So keep those oxygen scavenger residuals up. Make sure your deaerator is functioning properly. Do your tests. Don't fake your tests. Some people are famous for faking tests. So where do we see O2 corrosion? Well, let's look at our feed water path. Feed waters are going to come in here. It's going to go through an economizer. Then from the economizer, it's going to go into the steam drum. And then what we're going to have is a downcomer. Okay, in our normal boiler water level. So it is most active in the hottest locations, because we know what happens with dissolved O2. The O2 solubility, so let's say parts per billion here, and degrees Celsius here, you know, once we get to 120 degrees Celsius, our solubility is like nada. And, you know, up here, somewhere like that, right? Let's say 0 degrees Celsius. And so what we get is this, you know, negative solubility curve. What this is really saying is the solubility decreases at higher temperature. So if this stuff is going to be soluble and active and acting on metal surfaces, if I got an economizer, that's the first hot water that the dissolved oxygen is going to meet, because it's heated up by the flue gas. So we're going to get lots of oxygen pitting in the economizer. And then in the drum, we'll get oxygen pitting closest to where the feed water is entering into the drum, and maybe extending down into the downcomer, because that's where the water goes next. So that's really the most vulnerable locations for O2 pitting. So you folks are familiar with sodium sulfite. We use that in boiler #1, boiler 1, boiler 2, and we use it in the 4th floor boilers. Okay, and what we find is that sodium sulfite doesn't react super well. And so to make it react faster, there'll be a catalyst that's added. Again, a catalyst, if you recall from chemistry, does not participate in the reaction other than it speeds up the reaction, but it doesn't actually participate in the actual reaction. It's not a reactant. So what happens when we add it? Well, we add Na2SO3, and we find some dissolved oxygen, and we end up with Na2SO4. So what is this? It's a dissolved solid. What's that? It's a dissolved solid. Some boilers are intolerant of dissolved solids. In particular, utility boilers, high pressure boilers, we want little, if no, dissolved solids in the boiler. We want ultra pure feed water and all that stuff. And so this is one of the drawbacks of sodium sulfite, is it adds to the TDS. If we have more TDS, we need to blow down more. And if our CBD is blowing down more, then we lose heat, we lose water, and we lose chemicals, and which really means we lose money. Okay, because we pay for the water, and we pay for the sewer rates, and we pay for the fuel, and we pay for the chemicals. So ideally, we would like to have very low TDS in our feed water, low TDS in the boiler, and do less continuous blowdown. Now then, the next drawback about sodium sulfite is operating pressure. Over 6 megapascals, sodium sulfite turns into SO2 and H2S in the boiler, and this is bad. Notice that sulfur dioxide and H2S gas, these are bad things. We don't like them. So one alternative then is hydrazine, and I like to talk about hydrazine because I really like it, because this in fact was the stuff that we used at the generating station, and unfortunately there are not a lot of plants that use it anymore because it's toxic. But we looked at this already. The hydrazine plus oxygen gives you water and nitrogen, and then we get the bonus conversion of hematite to magnetite, which is really good for us. But there are some other things that we could use as well besides hydrazine. What are we using before, by the way?
DEHA.
Yes, DHA. And so the interesting thing about DHA, do you know what it turns into inside the boiler? Inside the boiler, it turns into hydrazine. Isn't that crazy? Do some research, check out the reactions. It's interesting. So next is carbon dioxide. Carbon dioxide potential. That's a term you're going to hear me use over and over again, and it really means any kind of CO2 or HCO3 ions that we get going into the boiler, whether it's calcium bicarbonate, magnesium bicarbonate, sodium bicarbonate, sodium carbonate, whether we're introducing it to the boiler or whether it's part of the chemical reactions in our little chemical factory. Anytime we got CO2 potential, it's going to cause carbon dioxide corrosion in the return lines. And if you take a look at this picture here, again from Suez, you can see from the inside of that condensate return line, you can see how it actually, and the acid attack exposed the threads from the inside. So basically what we get is, well, the term that they use is grooving, but the CO2 combines with the condensate and forms a carbonic acid, H2CO3. So how do we prevent this carbonic acid attack? By adding amines, either neutralizing or filming. What they have in common is that they are volatile. And some people think volatile means it goes on fire. Volatile means it becomes a gas, okay? It volatilizes due to the application of heat. So it's volatile, it turns into a gas and travels with the steam. And then when the steam condenses, it too condenses. And so the neutralizing amine, when it condenses, forms a basic compound that neutralizes carbonic acid. Oh, I don't even have to write it. It's the next line. It neutralizes the carbonic acid. Whereas the filming makes a physical film. It makes a barrier, it bonds to the metal. Now, the difference between the two is if this one here is a neutralizing amine, it's going to neutralize acid, which means that it's all about CO2. Whereas a filming amine, yes, will protect the metal from CO2, but also if there is oxygen, the potential for oxygen pitting to occur in the condensate lines, it also protects against that. Okay, so typically what we'll do is we'll have a blend of both of these, you know, a blend of some filming and some neutralizing amine. Now, there are certain advantages and disadvantages. Filming amines tend to plug things up. I remember it was my very first night shift on my own as a shift engineer at the Red River College powerhouse. And we had this stainless line that went from our, I guess it was the pressure transmitter for our boiler controls. And oh yes, this is what it was. It was our plant master pressure control. And the plant master pressure control, the little sensing line got plugged with amine. And I noticed that the boilers stopped responding correctly because it could not properly detect the boiler pressure, the main header pressure. And I came close to tripping off the boilers. But what I did was I looked at the trends, I looked at the charts, I saw that the master pressure wasn't changing, so I went to look at the master pressure transmitter, and I did a quick little isolation lockout. I removed that stainless line, and it was plugged with amine. I cleaned out all the amine. Meanwhile, I got the boilers on hand now, so that they wouldn't sort of wander off on their own. So the boilers are on hand, and I isolated the plant master pressure control, cleaned out the sensing line, put it back into service. Meanwhile, I'm pooping my pants, and then in the morning when my relief came in, I told him what happened. And he was actually a little bit skeptical. He thought maybe I wasn't ready to take on a shift. And then after he heard my story, he was quite impressed, and he realized, yeah, this guy can actually handle the shift. So it was kind of a cool thing. So anyway, filming amines do tend to plug stuff off, so you got to be kind of careful with it. But often we have a blend of filming and neutralizing. So the next thing is carryover, and carryover is moisture, right? Well, carryover is defined as any solid, such as a dissolved solid, or liquid, such as water, or vaporous contaminant, such as silica, CO2. Okay, so various things are all under this category of carryover. So anything that leaves the boiler steam drum with the steam. And we have this term that we call steam purity. And I think that in this chapter they talk about testing steam purity and stuff like that. I'm not going to go into it, but you can certainly read it over. But pure steam doesn't have any silica, CO2, this type of stuff. And again, it's from my go-to publication from Suez. And this is an overheated superheated tube. How did this happen? Well, because we had moisture that left the steam drum. So let's say that we had, really 99.9% dry and saturated. Really, really good. What do you guys get from boiler number 4? You guys have done the calorimeter. What's our dryness fraction for boiler number 4? Have you done that, or do you do that next term?
Yeah, we haven't done the calorimeter.
Okay, so next term you're going to be doing that. You'll be determining dryness fraction. So 99.9% dry and saturated, that's pretty darn good, but that means 0.1% is water. And what's in that water? Oh, dissolved solids, such as scale-forming compounds. And then what we do is we put it into a superheater, and this is what we get. And of course, because superheaters are only kept cool with steam flow, they don't have water in them, they overheat and then they die, just like this one did. This is a dead pipe. Now, we talk about silica, SiO2, and people say, oh yeah, it causes turbine blade. It's hard scale. Yeah, it does. Look. This is awesome. I just love this picture. That's silica dioxide. In other words, glass, right? Because that's what silica dioxide is glass or sand. When you walk down the beach in Cuba, you're walking on silica dioxide. Quartz, it's in your watch, okay? Silicon dioxide. So if this stuff gets carried over, it actually precipitates on the turbine blading, and it causes obstructions to the steam. We want the steam to be flowing through here, but now the passageways between the blades, when it's clean, there's that much room for the steam to go through, but then you build up the silica. I'm exaggerating, but now our flow passage is much less, so we get our power goes down, our efficiency goes down, our costs go up. Okay, maybe we got imbalance on the turbine. And of course, there's the cleaning expense, which includes downtime. So silica is a real big problem in thermal generating plants, but it's also a big problem if you work in SAGD. In SAGD, your boilers are OTSGs, once through steam generators, and because the makeup water usually has a lot of silica in it, it's brackish water, we get very hard scale. Not only hard scale in the boiler, but hard to remove scale. Silica scale is very hard to remove from a boiler. So, what causes carryover? Broken steam separation equipment inside your drum. Okay, so you are going to have some sort of baffle, and maybe you've got a cyclone separator, and maybe you've got chevron dryers, and maybe you've got a silica washer. Maybe you've got some wash water going on in there. And so all of these steam separation internal equipment, if you got something that's broken, you got a cyclone that has come loose and it's not separating them properly, or it's corroded and it's not imparting the proper spin. All of these things can cause carryover. We talk about alkalinity causing return line corrosion, but alkalinity makes foam because it is soapy. Okay, so high alkalinity and high TDS cause foaming, priming, misting. We've got organics, we mean hydrocarbon stuff, so anything oily. Boiler design. So a boiler design is designed for a particular pressure. It's got a particular steam drum size, so this boiler here's got a very small steam drum. Pardon me. This one's got a much bigger steam drum. This one here's got a very small disengaging space for water particles to leave the surface of the water as it boils. This one here got a very large disengaging space. So diameter of the steam drum, the type of the drum internals, the operating pressure of the boiler. This boiler here might be operating at a very high pressure, and at a very high pressure, the density difference between the gas and the water isn't that great, so that the water particles don't disengage very well. We'll take a look at this stuff a lot more next term when we go into boiler designs. And of course, as steam load increases, we can get swell. So sometimes not much we can do about that, but we can do something about malfunctioning water level controls. So one of the things we always do is we check our water level controls, make sure they're working correctly when we're operating the boiler. So how do we prevent carryover? We avoid sudden load increases. We don't exceed the boiler firing rate. Maintain the correct boiler water level. Check and repair the steam drum internal. Maintain the feeder water control system. Keep organics out. Control your TDS. Control your alkalinity and pH. And if worst comes to worst, last resort, we can add an anti-foam. So last resort, we don't want to get that far.